Hello, everyone. My name is Bergquist. I've been in the Hofstetter lab this summer, and today I'm going to tell you about our lab's experiments in segmental hemodynamic changes after cervical spinal cord injury. So each year there are 17,000 new cases of spinal cord injury in the U.S., the majority of which are cervical. And cervical spinal cord injury not only affects the voluntary movement of your arms and your legs, but it also inhibits all control of your torso. So that's autonomic functions such as breathing, bowel and bladder control, sexual function, and others. And we typically, in research of spinal cord injury, break the injury down into two parts, as Christine mentioned earlier. So we have the primary spinal cord injury, which is just the mechanical damage to neural tissue, and we have the secondary injury, which is a broad category of all of the pathological damage to neural tissue after the mechanical impact. Research on neuroprotectant treatments after SCI typically focus on the secondary injury because it's hard to go back and undo the mechanical damage after it's already done. And in our lab, we study, specifically in the secondary injury, we study visualizing the hemodynamics after spinal cord injury, so how your blood flow is changing afterwards near the injury. To do this, we use a novel ultra-fast contrast-enhanced ultrasound imaging system, which if you see, on the left here, that's what people typically think of as ultrasound. So you can see big structures, you can see kind of the shapes and outlines, but in our system, it's more of a functional ultrasound instead, so we can see more detailed flow velocities. And we do this using nonlinear pulsing sequences, ultra-fast plane wave acquisitions, Doppler SPD sequencing. And these things allow us to see tissue perfusion, which is blood flow through the microcirculation, and it allows us to see this. So this is our perfusion, separately from our macrocirculation. And right now, nobody else can do this. And because it's such a huge impact, or it has such a huge impact on how cells can recover after an injury, it's very important for us to understand how these tissue perfusion changes can change after injury as the injury progresses. And so previously in our lab, we've studied spinal cord injury tissue perfusion after thoracic injuries, but because it's cervical injury is so widespread, it's important for us to study this one as well. And we've seen that tissue perfusion on the left here, when we correlate tissue perfusion with BVD score, which is a functional measure of how well an animal can recover after an injury, we see that tissue perfusion is actually a better predictor of how well animals can recover after injury than even the force that the animal is injured with, which is really helpful because we can't really measure, go back in time and measure the force that someone got injured with, but when they're in the clinic, we can measure with our system how their tissue is perfusing and see how they're going to do later. And so our unique ability to visualize this perfusion deficit and the correlated functional outcome definitely has meaningful impact for cervical spinal cord injury patients. So in our study, we performed cervical laminectomies, did pre-injury ultrasound acquisitions, and then performed a unilateral contusion injury on C5, which is in the cervical spine, and then afterwards did post-injury ultrasound acquisitions. After we acquired all of our data, we measured the area of perfusion deficit in longitudinal acquisitions. So if we're looking at, this is our spinal cord the long way, your head is over here, your tail is over here. And we cut it straight down the midline, and then next to the midline parallel. We measured the area that way, and then we did cross sections as well. So just chopping the spinal cord this way, this way, this way, and looking at the area of perfusion deficit, not only in the injured segment, but also in the ones above and below it. And then we also measured the cross-sectional area of just the spinal cord itself. And what we have found is, here are some of our images of ultrasound. Left is pre-injury and right is post-injury. And And we found that the area of perfusion deficit, the average was 5 millimeters squared, pretty consistently across our animals. And we were able to see, but it's still difficult to visualize how the perfusion deficit acts kind of within the same segment, and then how it might impact the cells in that segment, since we can't see specifically where things are in our longitudinal acquisitions. So we experimented with taking cross-sectional acquisitions with good success. So the yellow circles here indicate where the spinal cord is. It's not taking up the whole frame anymore. And we found that on average, the area of perfusion deficit was 3.2 millimeters squared. And again, it was fairly consistent, but we're also able to better visualize the shape of the injury. And then from that, because we can see kind of the differences between the brighter areas get more blood flow and the darker areas get less blood flow, so that's gray matter and white matter on the outside. We can see kind of where our perfusion deficit, circled in red, is impacting the tissue itself, and then potentially they may be able to use that to inform neuroprotective research later. And not only are we able to see perfusion deficits in the injured tissue, we can also see it above and below our injured area. So C5 is where we have our injuries, and C4 is closer to the head, and C6 is closer to the tail. And we saw that the perfusion deficit area at C5 is significantly higher than at C4 or at C6. And we also saw that C4 tended to have greater perfusion deficit area than C6, which is consistent with what we saw in our longitudinal acquisitions, where with the head over here and the tail over here, our perfusion deficit tended to move more towards the head than it did towards the tail. We can also look at the area of the spinal cord itself to understand, we're beginning to understand the swelling and how our spared tissue could look after injury. So what we see here in this graph is that C5, the contralesional area, so the blue side of the spinal cord that wasn't the side that we hit when we injured it, this had significantly lower area, and the ipsilesional side was significantly larger in the injured section, but we didn't see that difference in sections or in segments above and below the injury. And from here, we intend to compare not just the total size of the halves, we also intend to compare just this space between the red and the yellow, so that's our spared tissue, to across segments, so we can see how much tissue is surviving, because that's what we can really treat in the clinic. And also, we intend to look at the area of the yellow, so the injured side compared to before the injury, to understand swelling and how that can potentially affect the intraspinal pressure after injury. So moving forward, we're going to look at 3D volume analysis, so not just the area of the perfusion, but also the shape of the injury, which is rendered here from our cross-sectional acquisitions. And we will also understand the perfusion deficits, to understand the salvageable tissue and predict patients' outcomes, so that physicians can be better informed to treat SCI patients to improve their quality of life. So a huge thank you to my lab mentors, Dr. Hofstetter, Dr. Kine, and Lindsay Cates for making this whole summer possible, as well as Dr. and Mrs. Ellen Bowden for being on this program, Julie and Sylvia for all the day-to-day things that we've had questions about. Thank you.